Welcome to the Group 39 summary video of a modern Nixie clock. The Nixie clock gets its name from the Nixie tubes that make up each of the digits of the clock. Nixie tubes were manufactured from the 1950s to about the 1990s when LEDs became cheap enough to replace them in the general market. Today, the Nixie clock is a really popular project for hobbyists. You get a really cool looking clock, it's a retro look, get nice glow of the bulbs, and it's a really good final looking product. Nixie tubes were made mostly in Russia. The technology behind the Nixie tube is a high voltage cold cathode tube with filaments bent to make the numbers 0 through 9 inside the glass. By passing a current through just one of the tubes, we can light up any number we want. You can multiplex 6 tubes together and add a little software to make a modern Nixie clock.
I'm Nicholas Brown-Tychus.
I'm Zachary Nielsen.
And I'm Peter Kessinger. Our project was sponsored by a professor here at Oregon State University who has always wanted to build himself a Nixie clock but never got around to it. Some of the project requirements that he laid out for us were it must have time settings that's both settable by mechanical buttons and an Android app with wireless capabilities. We chose Bluetooth. There must be an anti-cathode poisoning routine to extend the life of the tubes. There must be a case that the whole clock can fit into. It must be powered from the wall conveniently. Mechanical buttons must also display the date on command. Lastly, there is an RTC, which is keeping track of the time, which can also keep track of the time while the clock is not plugged into the wall. My contribution to the project was developing the Bluetooth app that could communicate wirelessly with the clock, the general clock code that was put onto the microcontroller that interfaced everything on the clock, and lastly, the RTC code that would store the time on a chip that was interfaced over the I2C bus. As you can see here, we have an Android app that is able to control the Nixie clock wirelessly. You can turn it on and off the LEDs, change the brightness, change colors. You can also set the time manually or sync it to the exact time on the phone, as well as switch between 12 and 24-hour mode.
I worked on 3 aspects of the Nixie tube project. First was case design, second was the Nixie tube multiplexer circuit, and the third was the LED underlighting. For the case design, the main challenge was just figuring out the exact size we needed to fit all the hardware in the box without having too much empty space. I needed holes for the Nixie tubes, the 2 encoders, and a power supply jack on the back. My second contribution to the project was the Nixie tube multiplexer circuit. This is required because we only have one Nixie tube driver, so we can only have one bulb on at a time. In order to make it look like all of them are on at a time, we need to scan through the digits fast enough so that our eyes can't tell the difference. To do this, we need to select one bulb at a time with the microcontroller. The 2 biggest challenges to this circuit are limiting the current through the anode of each Nixie tube and figuring out how to select each Nixie tube with a 5-volt output pin when the Nixie tubes take in 170 volts. As you can see here, this 5-volt line from the microcontroller output pin turns on this BJT, which in turn turns on the anode BJT for each Nixie tube, which allows current to flow through the anode. My third contribution for this project was the hardware and software for the LED underlighting block. On the hardware side, the circuit is fairly straightforward. The microcontroller controls which LEDs are on via these 3 BJTs. The current through each color is limited by these 3 resistors. You may notice that this resistor value is larger than the other 2. This is because the forward voltage of the red LED is lower than of the green and the blue. On the software side, I configured 3 separate PWMs for the 3 output pins to control the relative brightness of each color.
My contribution to the project was the high voltage power supply to supply 170 volts to the Nixie tubes. I did a large portion of the CAD work, which included drawing the schematic and then also doing up the PCB. And then lastly, I did the hardware settings code so that you can set all of the settings from the encoders on the front of the Nixie tube clock. The main challenge with the PCB had to do with the Nixie tubes. They had to be aligned such that you could see them from far away and it was clear which group of 2 was the hours, minutes, and seconds. So their position was fixed on the board and everything had to be designed around them. Likewise, the LEDs had to be placed underneath the Nixie tubes, and they're surface mount, so we had to leave enough space for the traces to get where they needed to go, but try to get them as close as possible to the back of the Nixie tubes. Another challenge with the board was that we had to custom make many of the footprints for these components. Nixie tubes are not so common as to have a publicly shared library, and many of these components needed to be resized. On top of that, there are over 100 components on here that needed to be hand soldered, which took a very long time and opened the door to lots of errors, but with continuity checking, everything turned out all right. So one of the most basic features of the clock is that it will keep its time once you unplug it and plug it back in case you have to move it across the room or a power outage or something. It's conveniently powered off of 9 volts from the wall. It pulls it straight from a wall wart. We get 9 volts into the back. As you can see, the time has stayed the same. You can go into settings by pushing the right encoder, and whatever is flashing is what you're going to change if you push the right encoder again. So here the time is flashing, now the date is flashing, and the LEDs in the back are flashing. So we can go ahead and enter the time, and then we can select which hours, minutes, or 12 and 24 hour mode. If we back out, we can do the same thing to the date, only this will change the year instead of 12 and 24 hour mode. Going to the LEDs, the default is off, and by scrolling through the different colors, you can see all we have to offer. The left encoder will change the brightness, so we can turn the brightness way down, or we can turn it all the way up. The default is right about in the middle. Now, if you don't want to mess with the encoders to change the time, you can instead use the Bluetooth app.
Here we go. You first have to connect to your Bluetooth app. However, if you're not connected, it'll have this little indication saying, hey, you're not connected, you need to connect first. So you hit that button, you connect to your device, and it says it's connecting, and now it's connected. You can again control the LEDs from here, brightness, which I've showed you this before, but then in more detail, I'll talk about this sync time functionality. So currently you can do this manual set time, which maybe you want your clock to be set a couple minutes fast, so you can do that, or you can get it synced down to the second by hitting the sync time button. So now whatever your phone time has is what your clock has. You can also then switch that between 12 and 24 hour mode. If you're in 24 hour mode, you can set the time, and as you can see, it shows 21:18 instead of 9:18. We'll go ahead and sync that up and call it good.
The first thing we did after selecting our project was to sit down with our sponsor Victor and go over all of his requirements for the project. Next, we met as a group and picked which requirements we wanted to tackle first. First thing we chose was the Android app. None of us had any experience with the mobile app, so we decided to get this out of the way early and not save it for last. The next was the hardware circuit design. We couldn't test any of our blocks or any of our software until the actual hardware design was done. And the last thing was the PCB. We ordered the PCB from China, and it takes a long time to produce and a long time to get to the US. So getting this out of the way early allowed us to test all of our blocks separately and together.
One of the difficulties that I faced in programming the microcontroller on the Nixie clock was keeping track of the time from the RTC as well as displaying it to the user and being able to write the time to the RTC whenever the user prompted. The difficulty came because the RTC chip was on an I2C bus, which made it very difficult because there are very specific protocols that the RTC requires in order to keep track of time accurately. For example, when you're setting 2 o'clock, it needs to know AM or PM unless you're in 12 or 24 hour mode. This made it very complicated because the microcontroller had to keep track of a ton of different variables and send all those variables correctly in a specific order for the RTC to keep this accurate time. But in the end, it ended up working out great, and the RTC and microcontroller were able to keep track of time and display it to the users.
When we were assembling the PCB, we ran into a really scary issue where one of the most important pieces of the system wasn't working at all, and that's the high voltage power supply. We didn't know if this was because we had messed up the schematic or if a trace had grounded and fried the whole board. So we set to work troubleshooting. In the end, it actually turned out to be a bad 555 chip. So we just replaced the chip and everything worked out fantastically.
We had a couple small issues with the case. The first of which was with the encoders. Each encoder has a small pin along the outside that prevents it from spinning. We didn't put a hole in the case to account for this, so over time the encoders could potentially come loose. We ended up tightening the encoders enough so that hopefully this does not happen. There's also one small issue with the location and size of the power connector in the back. Because the top is completely flush with the hole, it makes it very difficult to put the top piece in or to take it out. If anything goes wrong on the inside, this makes it a little bit annoying to take it out of the case.
And that's our project. We learned a lot making it and made a quality product in the end. For anyone taking the class in the future, we have some suggestions. First, do something that you're really interested in. We all chose this software intensive project because we really enjoy software. But we had enough hardware background that we could make a good PCB and just an overall good system. Another thing that we enjoyed doing was working with an OSU professor as our sponsor. He was able to talk with us in person often because he's always on campus, as well as was really interested in our project.
Thanks for watching.